Guys, welcome to the next lecture from Introductory Statistics. We have been working on the concept of random variables. Today, let's get a little deeper into discrete random variables. Let me start with an example. Suppose that a business has just purchased 4 laser printers and let us assume X, the random variable, is the number among these printers that require service during the warranty period. So tell me something, what values can X take? Well, if X is the number of printers that can require service in the period of warranty, that means maybe none of them require service. So 0, it can take value 0. Maybe just one of them requires service. Maybe 2 of them, maybe 3 of them, maybe 4 of them. Can X take the number 5? No, because there are only 4 printers. So X cannot be 5, right? So this is what is a random variable. An experiment happens. Within that experiment, you can generate a variable which takes certain real numbers. In case of discrete random variables, it will take some integer values, okay? Discrete values. And here, like in this example, whatever X I took, it can take values 0, 1, 2, 3, 4, which will be called like a range of X. X is a function whose range is 0, 1, 2, 3, 4. There isn't any other number that can come in here. X takes 0, 1, 2, 3, 4 in this experiment. Now recall, every value that the random variable takes, it is directly related to the outcomes in your sample space, right? So therefore, each value of X occurs with some probability. And hence there is notion of a probability distribution. Now, what will probability distribution give us? It will tell us how much probability is attached to every value that X is taking. Like in this example, X is taking value 0, 1, 2, 3, so on and so forth. So probability distribution will attach a probability, that is probability X is equal to value X. This is for the random variable. And this is for the value that the random variable takes. Many a times, this is also denoted as lowercase p and the value X. So probability X is equal to X, which can also be denoted as Px. If X is taking value 0, then this means this will be P0. X is taking 1, it is P1. P2 in case of 2, P3, P4. Where all these are probabilities, so they will be between 0 to 1. Okay, between 0 to 1. So what is happening in a probability distribution? You put up the values that your random variable X is taking and associate it to the probability that it is attached with. Okay, the entire sample space should be distributed in this table. The entire set of outcomes should be a part of this table. Let me give you another example where let's take certain values. Suppose a statistics lab has 6 computers, okay? Let's take a random variable out here. This is the number of these computers that are in use at a particular time of day. Now, number of these computers, since number of computers could be 1, 2, 3, 4, 0 for that matter, which is in use, right? So that means this is a discrete random variable. It's taking values 0, 1, 2, 3, so on and so forth. Okay, let's try to see with this example what a probability distribution could look like. A probability distribution table looks like the following. So it contains value that this random variable X can take. First thing is that you should be clear what values can X take. X could be 0 because maybe none of the computers are in use. 1 computer, 2 computer till 6. Can it take value 7? Absolutely not. Even if you write down that X is equal to 7, the probability attached to it will be 0 because X cannot be 7. You don't have 7 computers that could be used, right? You just have at the max 6 computers. So 0 to 6 is the value that X can take. Now X can take these values with certain probabilities. assume these probabilities. Let the probability that x is equal to 0 be 5%, so 0.05 here. 10% for 1, probability that x is taking value 2 is 0.15. Let's take 0.25 for 3. Let's take 0.2 for 4. Let's take 0.15 for 5. And let's take 0.1 for 6. Now, what is the use of this distribution table? The probability distribution table actually lets you calculate any probability of concern. So suppose we want to calculate certain probabilities. For example, let's take a question. Find the probability that at most 2 computers are in use at this particular moment. 2 computers at most. When they say at most 2 computers, that means at the maximum 2 computers. That means 0 computers could be at use. 1 computer could be at use, 2 computers could be at use. Okay. Probability that at most 2 computers are in use is same as saying probability x is less than or equal to 2. Less than or equal to 2 includes x being 0, or x could be 1, or x could be 2. Any case, right? Now, x equals to 0 or x equal to 1, what does it tell you? Or in set theory and probability means union. So, x equal to 0, union x equal to 1, union x equal to 2. Now, if you look at these as events, when x is equal to 0, x cannot be equal to 1. When x is equal to 0, 1, it cannot be equal to 2. That means these are all mutually exclusive. There could not be any intersections. So, therefore, this would be nothing but probability x equal to 0 plus probability x equal to 1 plus probability x equal to 2. Now, from the table, you can get the values 0.05 plus 0.10 plus 0.15. Probability that x is less than or equal to 2 is 0.3 or 30% chance. Okay. Similarly, you can also find out any other probability associated to this experiment, this random variable. Suppose we want to find out what is the probability that x is between 2 to 5. So that would mean this is equal to probability x is equal to 2. It could be x equal to 3. It could be x equal to 4 since it's equal to 5. So yes, you have to take the case of 5 as well. So this will be probability x equal to 2 plus probability x equal to 3 plus probability x equal to 4 plus probability x equal to 5. And from the table, you can get the total of these 4 positions, and that can give you your answer. So 0.4, 0.6, 0.75, 0.75, that means 75% chance that x would lie between 2 to 5 at this moment. Okay. If this is the probability distribution given to you. Had it been some other distribution, it would have been a different answer. So probability distribution table just gives you all the probabilities attached to the possible values that x can take. You have to consider all possible values that x can take, and according to whatever is your experiment, the probabilities attached to it. Now, the most important part of a probability distribution table is that if your distribution is correct. Now, when I say if your distribution is correct, that means you have taken all possible values of x. Okay. Now, if you've taken all possible values of x, that means you must have taken care of, or you must have distributed all outcomes in the given sample space, the sample space, whatever it could have been. Which means if all possible outcomes have been taken care of, are a part of this table basically, then that means this sum of all the probabilities, this has to be equal to 1, because what you've done is From your sample space, you have taken care of each and every outcome. Each and every outcome is a part of this distribution. If that's the case, then the probabilities attached to it should give you 100%, right? Because 100% has been taken care of. Thus, kindly write down a distribution needs to consider every outcome in the sample space. Therefore, the sum of all these probabilities have to be equal to 1. If it is not equal to 1, that means there is some problem with your distribution. The distribution might not be correct. There's another very important vocabulary associated to probability distribution, associated to the random variables. That is the probability mass function. Probability mass function or distribution function. Now, what is probability distribution function or probability mass function? Probability x is equal to x, something which we are writing as lowercase px also. Now, this is probability mass function. It can also be written as a formula for that matter. In a lot of examples, you will be able to give a formula to it. And therefore, the word function out here because there could be a formula given to it. Even if you're not giving any formula, then also every px that you see here, remember in the first example, I had written it like this. So every px, p0, p1, this is probability distribution function. Probability distribution function is associated to the probability distribution. So at every position that you have in the distribution, that is probability mass function. So therefore, when you sum it up over all the x's, when you sum it up, what you should get is 1. And of course, since a probability mass function is actually a probability, so therefore it has to be greater than or equal to 0. So probability mass function is, you can write it down as lowercase f. This capital X is for the random variable. This is for the value. Capital X is for random variable. This is for value. Fxx is, it's also written a lot of times as fxx or lowercase px. Basically, it is probability x equal to x. If x belongs to the range of the random variable x, that is, x takes the value of x. Okay. Example, let's try to create a probability distribution table and the probability mass function to be clear with this concept. I have an unfair coin for which probability heads is equal to p. So that means probability tails will be equal to 1 minus p. P stands for probability, so it's between 0 to 1. It's not equal to 0, it's not equal to 1, it's between 0 to 1. I toss the coin repeatedly until I observe a heads for the first time. Let y be the total number of coin tosses. Okay, so the total number of tosses that I make. Find the distribution. So first of all, we need to realize what values can y take and how this y can be generated. So y can take 1. That means 1 toss. Can y take the value 0? It will not make any sense because 0 toss will not make any sense. If I have a coin, I am tossing. That's the experiment all about, right? So y can take the value 1. It will start with 1. So y taking the value 1. Now, with every value of the random variable, you have a probability attached to it. Let's generate this probability. So y can take the value 1, 2, 3, 4, so on and so forth. Maybe I'd never stop, Now, if it takes the value 1, that means I'm just tossing 1. Why would I stop at 1? The whole idea is that I keep on tossing till I get heads, right? If I get heads at the first go, that I will stop, right? So this will happen when I am actually getting heads in my first toss, right? So probability y is equal to 1 is basically probability of the outcome heads. And that is nothing but p. It's not half this time, it's an unfair coin, okay? So it's p. Y is equal to 2. That means I'm tossing 2 times. Why am I tossing 2 times? Because I'll be getting my first head in my second toss. That means probability Y is equal to 2 is the probability of the outcome tail and then heads. I'm getting heads at the second go. So that will be 1 minus P into P. The next is y equals to 3. Now, y is equal to 3 means I'm tossing 3 times. Why am I tossing 3 times? Because I'm getting heads for the first time at my third trial. So that means probability TTH, that means 1 minus P to the power 2, because 2 times tails and then P. So on and so forth automatically. Can you see for y equals to 4, 1 minus p to the power 3 into p. So do you understand now how we can generalize this? If I take the case where y is taking the value n, that means this will be a case where I am getting tails for n minus 1 times, and on the nth toss, I'm getting heads, right? So the answer will be, the probability attached to it will be 1 minus p to the power n minus 1 into p. So which means that I can actually generate a formula for this scenario. If I write down n here, it is 1 minus p to the power n minus 1 into p, where n can take what values? N can take value 1, 2, 3, so on and so forth. I can keep on going. And this, my friends, is your probability mass or probability distribution function. I wanted to generate a formula for you so that you can relate with it a little more. So probability distribution function, one and the same thing as such. Always remember, whenever we're talking about probability distribution, that means you are taking care of the entire sample space. Then only it's a correct distribution. Thank you very much. I hope this will really help you guys. Thank you.